Okay, so let's start with the first problem that we were given for week 4 programming assignment. So the question states that we are given two permutations A and B. Both the length of both are n, and permutation is basically an array consisting of n distinct integers from 1 to n in arbitrary order. And what we have to do is, like, we are given another permutation x, we're given A and B and the permutation X such that it contains values at some positions in permutation C. Basically, X can be for any ith position, Xi can be 0, AI, or BI for any I. And then there is no, okay, yeah. So we have to determine the number of different possible permutations of C. And C has to be a permutation. Okay. So let's just take an example. If we were given A as given A as 2, 3, 1, and B as 3, 3, 1, 2. Okay, so here, and the X permutation is given to us 0, 0, 0. Now we have to determine the number of permutations possible for C. Now let's assume that for the first position we take the first element of A, that is 2, reconstructing C. And if we observe, if we have taken 2 at the first position, then we can, for the third position we cannot take 2. So for the third position we'll take it as 1, because 2 cannot come, because it's a permutation. All the integers in a permutation should be distinct, and so that is why here 1, and finally only one element is left, that is 3. If the second permutation we can consider is take 3 at the first position. If we take 3 at the second position, you can see we cannot take 1, we cannot take 3 again, so we have to take 1, and then 2 is left. So in this case, a total of 2 permutations are possible for C. So let's start by coming up with an approach for this question. So let's first solve the version of this problem where the array X only consists of zeros. There are no AI or BI at any position, and it only consists of 0. And this means there is no constraint on the permutation C that's need to be formed. Okay, so let's say we have a permutation for A as 1, 2, 3, and 4. And for the permutation B, we have 3, 1, 2, 4. Okay. And now, as stated already, that we are considering the case where the X array that was given is only consists of zeros. Okay. Now, suppose that we have chosen the first element of array C. For the array C, we have chosen the first element as the first element of array A, that is 1. So if we have chosen the first element of array A, we cannot choose the first element of array B for the first position, right? Because see, if we have chosen 1, then we cannot choose 3. We have to choose only one of them. And since we want the array C to be a permutation, we have chosen it of 1. As we want the array C to be a permutation, we will have to get the first element of B from A, which is 3. So this 3 has to come somewhere in the permutation of C, because it's a permutation, right? So it has to come somewhere. if we search for 3 in the array A, it comes at the third position. As array A was also permutation, 3 only occurs once. As B is also permutation, 3 only occurs once. And we have to include 3 in our permutation of C. So at the third position, if you see, we have to include 3 over here. If we have chosen 1 here, and haven't chosen 3 from the first element of B, we have to choose 3 somewhere else, and 3 comes at the third position. So here we choose 3 and add it to array C. Now we won't be able to choose the element of B in the corresponding position. The corresponding position is this. At the third index, we cannot choose this element because we have already chosen 3. Right. And now, so we cannot choose 2 here. 2 has to come somewhere else. Then again, we can search the array A. We can search the array A. It comes at the second position. And now we add it to here. Right. And we add it to as C. And this time, if you see the element in B at the corresponding index is 1, which is already which has already been selected. And now we are not like constrained to select 1 at someplace else. So I hope this is making some sense, because so, and finally, okay, for this it is equal, so 4 has to come here. So I hope you're getting an intuition of what the approach is looking like, right? Let me make it just more. Okay, I'll just explain it further, because see, if we observe that the elements that we were constrained to choose from A were like along with the initial element, we selected 1, 2, 3. Right, we selected 1, 2, 3, and so it is a permutation of elements for from the starting to the third index. We chose 1, 2, 3, and we could have also chosen, if we had chosen 3, the permutation would look like something 3, 1, 2. So what you can just observe that if for this, if we just fix for this group of elements 1, 2, 3, if in C, if we just fix, like here we fixed 1, then we can know, like for the next, wherever 3 occurs, we have to fix 3 over there. And wherever for the corresponding index 2, we have to fix 2 at some place else. So the intuition is, like if we fix any one index at C, basically it is only further we don't need to check. It will be only a one permutation will be possible if once we fix a particular index in C. So so considering only a group of 1, 2, 3, these elements, if we fix 1 or we fix 2 or we fix 3, any of these in the permutation C, there will be only one resulting permutation. So here, when we fixed 1, we don't need to consider any, like we are not coming across case we could pick this or we could pick that. We were obliged to pick another element, right? So once we fix 1, or we could have fixed 3. Now for this group of 1, 2, 3 elements, all the other positions or corresponding indices are fixed now. So intuition is basically, if we can make some algorithm, come up with an algorithm such that we can identify a group of indices like 1, 2, 3. We can like come up with an algorithm so that we can figure out 1, 2, 3 is a group. Like 4 is not in this group of 1, 2, 3. If we can come up with an algorithm to find 1, 2, 3 is a group, then we know, like when we fix this in the permutation C, there will be only there will be only 2 possible permutations. One from the C, one from the B, and one from the A. Okay. So in this, when the X given to us, all the were filled, when the X was only filled with zeros, and if we count this a group, basically, then so in this version where X was only filled with zeros, we have to just count the number of groups of size bigger than 1. This is a group of size bigger than 1, of size 3. And we have to just count, okay, this group occurs once. So basically, answer is basically, we have to just count the number of groups of size bigger than 1. And if the such groups, basically there are P groups, just assume if there are P groups have inside the array, like 1, 2, 3 over here, and there could be other also. Here only there is one group. So if there were P groups, then just apply the concept of P and C. For each group, there are there are only two possible permutations, one from A, one from B. Right? We can for each group, there are only two permutations possible, and you can choose two permutations for each group. So 2B times, that is 2 power P. I hope this is clear, because we have just applied simple concept. You can say, okay, we have just counted the number of groups of size greater than 1. And if this is what 2 power P, we just count this. Yeah. So now second case where the X array is not just filled with zeros, there are also AI or BI occurring in that. In this, we just have to make sure that each group we count has zeros in all the corresponding indices of the group we are considering. So if, let me take another example from the okay. So this is one of the exam test cases that were given. So here, now, what groups can you see over here? I can see 1, 2, 3. This has a group. We can take 4. This has a group, and 5 and 6 has a group. Right? 1, 2, 3 is a group. 4 and 7 is a group. 5 and 6 is a group. Group is basically if you take 3 and the corresponding index is basically in the group, wherever it is occurring, it is not occurring outside that group. Right? 3 is not occurring anywhere here. So these are the groups that we can form. We'll come to the algorithm how to form these groups later. But if we form these groups 1, 2, 3, all of size 1, there are 3 groups, right? But now for the second condition, basically we are already fixed 2 over here or 1 over here. We already fixed 2 indices in for this group. So if you see, we have already fixed conditions, then only one permutation for this group is possible, not 2. Because even if we fix one index of this group, there will only be one permutation possible then, right? But for 4 and 7, there are 4, 7 for this group, there is no index fixed in the array X, right? So 2 permutations are possible here, and 2 permutations are possible here. So the answer should be 1 into 2 into 2, that is 4. Okay, so yep, this is how we what the algorithm is basically if we form these groups. Now to form these groups, how we're going to do that? There are many ways this can be implemented to form these groups and count this. But here we are going to use DSU, that is disjoint set union, and we'll union each group together like 1, 2, 3, and in the best possible way and implement this approach. Okay, we'll use DSU to form these groups, right? All right, so let's just come to the code directly, so that it would be more clearer in that way. So to here you can see, right? What we are doing is we have taken the inputs for everything, right? Here just we are decreasing the input. This is because because the values given to are from range 1 to n, but in the array n, the indexing is done from, it starts from 0. That is why we are reducing it. So whenever we have to access any index, we just, we don't need to worry about the out of bounds errors. So, yep, now here we are creating the array ds. We are getting an array for the disjoint sets where for any ith index, it will store its parent, its representative parent, right? So for in here, if we have formed the groups would look like some 1, 2, 3, right? Here it would be 4 and 7, 5 and 6, right? So this is what the DS array is doing. And now just here you can do, what you can do is for used, we are, okay. Now this array we are creating, we want to remove those which are already same. Basically, if you know, if AI and BI are same, then there is only one permutation possible. So just remove it from all other groups, that particular ith element index, that ith element, we can just remove it from all the groups. So that is why we're just marking as it is already been counted for used. Okay, we are making it as 1. It's just rather than this algorithm, okay, it would be better that way. Okay, so we were first, let's given 2, 3, 1, 4. And here we were given 3, 1, 2, 4. So now we have created another array ds, and initially all the indexes have -1. Basically every one is a parent of itself, and we have created another array used with 0 at all positions, right? Now we first, if you look, we need to remove 4 from our all the considerations, all the groups. So we'll just, in the used array, we'll mark it as 1. And any other occurrence where AI is equal to BI, right? This is what our code is doing. Here it's traversing from 1 to n, right? And it's marking for all AI equals to BI, used equals to 1 at that index. Okay. Now, what we have to do is, now we have to count the groups, right? Firstly, getting the group, basically forming the groups. So for all AI and BI, we're going to do the join operation of DSU. So I hope you remember what the join operation is going to give us, right? Once we call join for all AI and BI, here, like in this, we'll go from 0 to n, and we are calling join operation for all AI and BI. So once here I have implemented the DSU approaches here over here, the find function and the join function for DSU. Okay, so Once we do this join operation, the final DS that is going to look like is -2, 0, 0, and -1. Why this? Because this is a single group, and here 0 is going to the parent, and for the 1 and 2, the parent is going to be 0, right? And 4 is just another group, itself another group. If but I hope it's making sense. Okay, this is what is happening. And now next step is basically now we have to check. We'll take another input, that is the for the array X that was given to us. We need to take its input. We'll check. If it's 0, then we don't have to do anything. But if it's already fixed, anything except than 0, then we need to check if, okay. We'll just find C, basically we go to its parent, and we'll check if it's not already fixed. Basically, now what it's going to do is, just let's see. Okay. All right. Here A and B is given. For example, if X earlier that we took the case, it was given 0 at all positions. If we just take 2 over here, 0, 0, 0. Let's just take this example. Now, when we take the input, we'll take 2 as the input, and C will be 2. We reduce C to 1, right? And now we check, okay, 1 is greater than equal to 0. And when we call the find operation, when we call the find, right, we'll do the find operation for the index 1. So what is going to do? For 1, we know it's going to return 0 over here. And 0 used 0 is equal to 0, right? And now we just need to fix. What it's going to do is, now it sees, okay, used is equal to 0. Basically, it's not equal to 1. Used 0. So basically, C is now 1, and it will fixed used 1 equals to 0. Right? Basically, it will go to the parent of 1, that is for this. What is this doing? Find C. It finds the parent of C. C here is 1. It finds the parent of C, 0, fixes C equals to 0, then looks for use 0, that is equal to 1, that is equal to 0. Look over here. And not 1, basically it's not 0 equals to 1. It satisfies the condition. It goes into the if condition, and then it does used C equals to 1, used, that is used 0 equals to 1, used is equal to 1, right? It makes the parent of each group, that is whatever that group 1, 2, 3, it makes the parent equals to 1. So this loop is what it's doing, is basically it's traversing all the indexes. And if for a group, if X is already fixed, Xi is already fixed, one of AI or BI, for that group, it is making its parent equals to 1. So because once when we finally count the number of groups, what we are going to do is firstly check this condition, DSI less than 0. less than 0 means it is a parent of some group. Okay, DSI less than 0 means it is a parent of some group. Okay, and if it's not equal to 1, okay, that this means it's not equal to 1. Basically, here, if you say it's already equal to 1, right? This means the permutation for this group is possible is only 1, so we don't need to count it, right? So that is why it won't go into this loop. But if here for the earlier permutation, if if we remove this, if it was given 0 0 0, then this used array would look something like this, and DS would still look something like this. Okay, let's just finally, if array was if X was 0 0 0, DS would still look like -2 0 and -1, and our used would look like what it would look like. It would like 0 0 0 and 1, right? Because it's not fixed at this position. X1 is not fixed. It would look like this. So when we do for loop, for the first position, it's going to check DSI is less than 0. DSI is equal to -2, which is less than 0. And it is going to check used I equals to 0. Use 0 is equal to 0. Basically, it satisfies this condition. Then it goes into the if statement and multiplies our answer by 2. Right? We have to get 2 power p. So it multiplies our answer by 2. So our answer was earlier 1. The 1 permutation is always possible. It becomes now 1 into 2 equals to 2. Okay. Then for the second index, it sees DSI is not less than 0. What it means is basically it's not the parent of any group. It's a child, and it's not the parent of any group. Right? So we have to skip this. And for the DS3 third position, it sees is not less than 0. This means it's not a child. It's not a parent. It's a child. This means either the group that is the element that which group it's part of, it's either considered later or before it's already considered. We are not looking at the child. We're only looking at the parents of each group, because we need to count the number of groups that there are, right? This is not this child, so we'll skip this. Now it comes to 4, right? It comes to the fourth index. DSI is less than 0. Yes, this is a parent of a group. But here, if we check used 4 is equal to 1, used 4 equals to 1, this means this is because here we have checked the condition. A4 equals to B4, and we have marked it as 1, so that we don't multiply the answer again by 2, right? Because this group size is only 1. One permutation is only one permutation is possible for that. So that is why we get finally 2 as the answer. I hope this algorithm is clear to everyone. Fairly simple. What we are doing is just forming groups. Like we form the group for 1 2 3, another group, and 4 as another group. We're just counting these groups. And for X, if any was already fixed, like 2 was fixed, then we have instead of 2, we'll have 1 as the answer. And for this, we have only 1 as the answer, because the group size is less than it's only 1. It's not greater than 1. So yep, this was the DSU implementation for this question. There are other ways to implement this, to form the groups that we are forming, but DSU is one of the ways. So if you want to take another example and run it, basically this example that we have taken for this group, we have fixed it, right? Yep. So here, once we do the join operation, our disjoint set matrix and disjoint set array is going to look something like this after the join operation. Okay. What this is telling us, what this tells us, basically, it is looking like -2, 0, 0, -2, 4. Okay. Actually, -2, 4, and 3. So this means this is a parent of a group, this is a parent of a group, and this is a parent of the group. Rest are just children of that or of any groups. Okay. We're looking just as these in the final for loop. We are just looking at these indexes. And here we're just looking at that. And if you see used, what will be the use look like? Which one is the C? What will use look like? Uh, hmm. There seems to be some error. I don't know. But the used array would look like something like it would be a 1 over here, 0, 0, 0, 0, 0, 0. The used array would look like this. This is because we have already fixed. If you look in the test case, we have already fixed 2 over here at the first index. That is why we have marked it as 1. So when coming to this parent, we don't consider it. We just move on. Okay. And then we come to this. Here we'll look used is not equals to 1 at this position. So we'll consider it. We'll take 2 from here. Then we come here. We'll take 2 from here. Final would be 4. Yeah. This was the algorithm for the DSC implementation. Now just let's look at I'll just explain the week 5 programming assignment question 2 also. Okay, what this problem is saying is basically you have clicked some photos and it is in the form of a matrix. The photo is stored in the form of some matrix, 2D matrix of size m into n. Okay, and it filled with integer values. Integer value represents a color of a pixel or a cell, and you given the coordinates of the pixel, cell, and the color that you want to change. So we want to change the color of the pixel at x comma y to a new value. Earlier it was some integer I. We want to change it to x. Okay, but once we change to x, for all the adjacent same colored cells, basically all the cells whose color was I, surrounding it, touching that xy, we have to change it. We also change it to the 2x. Okay. Now, okay, let's just take another input example. Um, The matrix that we are given is this. Right. X is given as 3, Y is given as 2, and the new color is given as 4. Okay, from here. Now, for 3, 2, what is 3, 2? 1, 2, 3, 3, 3, 2. Okay, 3, 2 is this. Okay, 3, 2 is basically this index. Because indexing is start. It's said that indexing is done from 0. Okay, so this is 0, 1, 2, 3, and this is 0, 1, 2. Okay, sorry. This yeah. So the index is set, indexing is done from 0. So if you consider the row of 0, 1, 2, 3, and 0, 1, 2, this would be the pixel value, that this would be the pixel or the cell whose color we want to change it to 4. Earlier it is 2, right? Now we want to change it to 4. So if we change it to 4, right? Now of all its surrounding, you see 2, 2, 2, the same color of the surrounding pixels, that is 2. We also need to change it to 4. This also we need to change it to 4. Okay. Now you look at this 4, there is no 2 over here, right? So we'll stop here. But for this index, for this cell, there's a 2 over here. So its color also needs to be changed. For this 4, then this color needs to be changed. This color needs to be changed then. And this color is also needs to be changed. And now we have to stop. Okay, right? We have changed all the adjacent values of the cell. So this is what the problem is about. We have to then finally output the final configuration of this. The final configuration, what it would be? It would be 1, 4, 1, 2, 3, 5, 1, 4, 4, 4 again, 3, 4, 1, 4, 4, 4, 5, 4, 6. Remember that we started from here. We changed this value, we changed this value, then we changed this, we changed this, we changed this, and this. Rest is same. I hope this problem is clear to everyone. So this is the final configuration that you need to print as the output. Thank you. Sahil, now you can explain the week 4 programming of assignment 2 approach. Thank you.
Hello everyone, I hope my voice is audible. Yeah.
Yes, it's audible.
So, yeah, sure. So, if we talk about the week 4 programming question 2, it is based on the data structure disjoint set union, which is sometimes like very useful in competitive programming questions. So, let's take up the question. So, yeah. This is the question. So the question says you are given an undirected graph with n vertices, and each vertex represents a city. We say that city U and V belong to the same state if there is a path from U to V or V to U. Your task is to find out the number of states. So basically, a state is a group of directly or indirectly connected cities and no other cities outside of the group. So for example, if this is a city, this is a city, this is a city, this is a city, and these three are connected, then this is one state and this is second state. So the number of states here is equal to 2. So we just need to calculate the number of states. And if we look carefully at the constraints. So every time when you encounter a CP problem, you read the question, you read how the input is taken. It is very important to look at the constraints as well, because mostly in CP the time limit is given as 1 second, which means that you cannot have an algorithm which runs in which takes more than 10 power 8 operations most of the time. So yeah, that is like you need to keep in mind the constraints. So here the constraints are simple. T is the number of test cases, N are the number of uh, what do we call the cities, M are the number of edges between them, and U and V, obviously U and V are the cities which belong to 1 to N. Okay, so if we consider this test case, so this is one is the number of test case. We have 10 and 7. 10 is the number of edges, N equal to 10, and 7 is the number of edges, that is the paths between cities, so M equal to 7. And now these 7 lines contain cities U and V such that there is a direct path from U to V. Okay, so we have a path from 1 to 2, 2 to 3, 1 to 3, 4 to 5, 4 to 6, 5 to 6, 7 to 8, and we have 9 and 10 which are disconnected. Okay, so if we see here the number of states, these 3 cities belong to one state, these 3 cities belong to one state, these 2 cities belong to one state, this city is itself a state, this city is itself a state because 9 is disconnected from everyone, 10 is also itself a state because 10 is also disconnected from every other city. So there are number of states equal to 5. So here the answer is 5. We get the output as 5. Okay, so basically this is all about the question, a very easy question. You are given n vertices, m edges between them, you just need to find the number of connected components between them. This is a very famous question in CP and DSA. If you are preparing for your interviews as well, this is a basic. If you are encountering this question in an interview, then you should consider yourself as lucky, because this is one of the simplest question and you should know how to do it. So I'll tell you. So what we will do here is we will use the data structure which is disjoint set union data structure. So what it is all about. So let's say if we run this disjoint data structure on this example, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are 10 vertices. So what the disjoint set union says that we need to union those vertices which are connected with each other, right? So what we will do, like at first, when there is no edge between the vertices, every city is by itself a state, right? Every city is by itself a state. But when we add an edge 1 to 2, what happens? We combine these two. Okay, we combine these two. Then we add 2 to 3. So what happens? We add 3 to this 1 comma 2. So now this 1 2 3 is like these 1 2 3 are connected with each other. So this is what we are doing. We are picking 1 2 was already combined. Now what we are doing, we have to combine 2 and 3. So what we will do, we will perform a union operation and make it 1 2 3, right? So similarly we perform the union operations. So how will we know that if let's say U and V are given, how will we know that U belongs to a different set and V belongs to a different set and we have to union them? How will we know that U belongs to different set, V belongs to different set? So for that, like this is the basic algorithm. I will explain you the algorithm, how it is done. So what do we do? The algorithm goes as follows. We maintain a rank array and a parent array. Rank array and a parent array. What do we mean by rank array? What do we mean by parent array? Initially, 1 2 3 4 5 6 7 8 9 10. Initially, every point is parent of itself. So 1 is parent of 1, 2 is parent of 2, 3 is parent of 3, and so on. And initially, the rank of each point is 0. Rank of each point is 0. Okay. Now, what we will do, let's say if we want to union 1 and 2, what we will do, we will find the parent of 1, we will find the parent of 2. So what is the parent of 1? 1. What is the parent of 2? It is 2. Are these both different? Yes, they are different. So what we will do, if the parents of u and the parent of v is different, that means the both vertices belong to different sets and we need to union them. How will we union them? We will consider the rank. So what is the rank of 1? It is 0. What is the rank of 2? It is 0. Rank of both the vertices are 0. So what we will do, we will attach 2 to 1 and we will update the rank of 1. We will increment the rank of 1 by 1, so it will become 1, and rank of 2 remains 0. Okay. So what does rank mean? Rank means that how many vertices are connected. So rank of u is defined as that how many vertices are directly connected with u. Okay. So this is how we perform the operation. Let's say now 1 and 2 are connected. 3, 4, 5, 6, 7, 8, 9, 10. We have these vertices left. Now, if we want to add an edge between 2 and 3, what we will do? We will find the parent of 2. What is the parent of 2? Parent of 2 is 1. Right? Parent of 2 is 1. And what is the parent of 3? Parent of 3 is 3 only. So both these parents are different. So now we will perform a union operation. So we have found out that the parent of 2 is 1. So parent, we found out the parent of 2 as 1 and the parent of 3 as 3. Both these parents are different. So we know that these points belong to different sets. So we need to perform a union operation. Now parent of 2 is 1. So what is the rank of 1? What is the rank of 1? 1. And what is the rank of 3? It is 0. In the previous case, the ranks were similar. So we did what we did. We attached one of the vertices to the other vertex and we incremented the rank of the other vertex by 1. Okay. But here, if you see the rank, there is a difference. Rank of 1 is more than rank of 3. So what we will do? We will attach the vertex which has a lower rank to the vertex which has the higher rank. So what we will do? 1 is there, 2 was already attached to this. Now the 3 vertex which has a rank lesser than 1 will be attached to 1 and the parent of 3 will be updated to 1. So this is all about disjoint set union structure. Okay. So basically the word says disjoint set union. Let's say these are 3 sets. We have some vertices here, we have some vertices here, we have some vertices here. Every vertex here in this set will have some specific parent x. Every vertex here in this set will have a specific parent y, and every vertex here will have a specific parent z. So when and now if we want to see whether u and v belong to the same set or not, then we calculate the parent of u, we calculate the parent of v. If both the parents are same, then we know that both the vertices belong to the same set. If the parents are different, then we know that the sets to which they belong are different and we need to perform a union operation. Okay. So how do we perform a union operation? Is by like we have the parent of u, we have the parent of v, they both are different, and that is why we know that the sets to which these u and v belong are different. So we need to perform a union operation. We find the rank. Okay. We find the rank of parent of u, we find the rank of parent of v. If both the ranks are same, if both the ranks are equal, then what do we do? What do we do? Like, let's say if Yeah. So both the ranks are similar. Then what we will do is we will assign you, sorry, parent of U as parent of V, and we will update the rank of parent of U by 1. Okay, so we'll do this operation. That now we had U and we have this parent of U. So what we will do, we had V. Okay, we had V and we had this parent of V. Now these two belong to different sets, and we have found out that the rank of parent of U and rank of parent of V are same. So what do? We say that now the parent of V will be parent of U. Okay, so sorry, parent of V is parent of U. So we have attached V to this vertex, and we have incremented the rank of this vertex by 1. Okay, so this is how we perform the union operation if the ranks are equal. Let's say second case, case 2. This was case 1 when the ranks are same, and case 2 when, let's say, rank of one vertex, let's say rank of parent of U is greater than rank of parent of V. And what do? We attach V to parent of U. That means we make the parent of parent of V as parent of U, right? So if the rank of parent of U is more than rank of parent of V, then parent of U will become the parent of V. And we don't alter the rank of parent of U because it is already more. Okay, so this is the algorithm, DSU algorithm. Let's jump onto the code. In that way you will be able to understand easily. So in this question you just need to find the number of connected components. Okay, that means you just need to perform the disjoint set union whenever you encounter an edge, which is given in the test case. You just need to perform union, and at last whatever number of sets you end with, that is the answer. Okay, so let's jump onto the code. Yeah, so what we are doing, so if you see, we are taking t number of test cases, and then we are calling the test function. So here, this is the test function. We are taking n and m, which is n is the number of vertices and m are the number of edges. Okay, then we have a parent array, we have a rank array. Okay, and we are calling a function make set. So what we are doing, as I told you, that initially every vertex will be its parent. So parent of I is equal to I. That means parent of 1 is 1, parent of 2 is 2, parent of 3 is 3, and rank of each vertex is initialized to be 0. So rank of 1 is 0, rank of 2 is 0, and so on. So this is the initialization part. Now for each edge U and V, you find the parent of U, you find the parent of V. You find the parent of U, you find the parent of V. This is the find parent function. So the time complexity in which you can find the parent of a function is constant. So this is very important to note. How it is constant, that is a different thing. If I start to explain you why it is constant, that then this lecture would become very long, so I will not do that. But like, you just need to remember that the method to find the parent of a vertex is constant. Okay, as a time taken to find the parent of a vertex is constant. So this is the function by which we are finding the parent of a vertex. So what we are doing, when are we stopping? if node becomes equal to the parent of node, that means let's say if we had 1, 2 and 3. 3 was connected to 2 and this was this. So if we want to find the parent of 3, what we will do? We will go to 2 and then we will go to 1. So ultimately the parent of 3 is 1. Okay. So in this way, like we need to find the parent. So this is the find parent function. Like it's very easy to understand. So okay, so we find the parent of u, we find the parent of v. Now, if rank of u is less than rank of v, so what do? We assign the parent of u as v, and if uh, rank of v is less than rank of u, then we assign u as the parent of v. Okay, and if both the ranks are equal, rank of u is equal to rank of v, then what we are doing? We are assigning u as the parent of v, and we are updating the rank of u. So we had u, we had v. So what we are doing, the parent of v becomes u. So we update the rank of u by 1. Okay. So in this way, we will be able to perform the union operation. So this is all about union operation, how to do that. Okay. Now, so we had vertices. After performing the disjoint set union, we have set 1, we have set 2, we have set 3, we have set 4. Now we just want to calculate these number of sets. That is our answer. How will we do that? Let's say in an example, in this example, if we see, we have 1, 2, so we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we encounter 1, 2, parent of 1 is 1, parent of 2 is 2. They both are different. So what do? We assign 1 as the parent of 2. Okay, now 1 is the parent of 2, and rank of 1 is updated to 1. Okay, now if we see 2 and 3, so the parent of 2 is 1, the parent of 3 is 3, and the rank of 1 is more than rank of 3. So what do? Again, 1 will be assigned as the parent of 3. 1 is assigned as parent of 3. Now we have 1, 3. So what is the parent of 1? It is 1. What is the parent of 3? It is 1. So both the parents are same. So we will not do anything. Okay, we will not do anything. Now we have 4 and 5. So parent of 4 is 4, parent of 5 is 5. Both the ranks are equal. So what do? We assign 4 as the parent of 5. 4 and 6, similarly, rank of 4, like the parent of 4 is 4, the parent of 6 is 6. Both are different. Rank of 4 is 1, which is more than rank of 6. So 4 is assigned as the parent of 6. And similarly for 5 and 6, the parent of 5 is 4, the parent of 6 is 4. So both the parents are same. So we need not do any union operation because both 5 and 6 belong to the same set. And then 7 and 8, 7 is assigned as the parent of 8. So you can see that these 3 are connected, these 3 are connected, these 2 are connected. 9 is not connected to anyone, 10 is not connected to anyone. So if we see, we have 5 sets. That means we have 5 connected components. That means we have 5 states. Okay, so that is why the answer is 5. Okay. After we have made all the sets, how do we calculate the number of connected components? So it is very simple. What do? We run through each vertex, and if I comma parent is equal to I, what does that mean? That if the node is parent of itself. Okay, so I will explain you this. If you see, 1 is the parent of 1. Who is the parent of 2? It is 1. Who is the parent of 3? It is 1. So we have 1, 1, 1. Parent of 4 is 4. Parent of 5 is 4. Parent of 6 is 4. Parent of 7 is 7. Parent of 8 is 7. Parent of 9 is 9. Parent of 10 is 10. So for a vertex I, if the parent is also I, if for any vertex, that vertex itself is the parent, we calculate such number of vertices, and that is the answer. See, if we traverse through every vertex, and if we see who is the parent of 1, okay, 1 is itself its parent. So we will we will take those vertices whose parents are they themselves, and we will calculate such number of vertices, and that will be our answer. Okay, because yeah, so like you can easily understand this, because if we consider these three, 1 is parent of itself, 2 is not a parent of itself, 3 is not a parent of itself. So we'll just take 1, we'll just take 4, we'll just take 7, we'll just take 9, we'll just take 10, and we count such number of vertices, and whatever is the count is the answer. So basically, this is how we can find the number of sets. So this is what we have done. We have found the number of vertices whose parents are they themselves, and we have just returned the count. So in this way, we have performed the disjoint set union. So it is a very simple very simple algorithm. You just need to understand and go through it once. And if you guys want to use this code as a template, you can just message me on Discord. I will send you the code. So this is a very useful code. I always use this code in my CP problems if I want to use DSU. Okay, so this was all about the programming question 2. Now let's try to look at week 5 question number 1. Okay, so what it says, so this question is based on this question is based on BFS/DFS. You can solve this question using any of the one algorithms. So what it says is, there are n towns in India and m bidirectional railways. Road networks are also exist between the towns. There exists a bidirectional road between X and Y. If and only if there is no railway between X and Y. So what is this? What does this mean? If we have X, we have Y, then either there will be a road between these two, or there will be a railway between these two. Okay, so at least any one of them will be there. Okay, so exactly one of them will be there. Either there will be a railway or there will be a road between these two. Okay, so a train and a car leave town 1 at the same time. They both want to reach the town N. Car can only travel through roads, obviously, and the train can only travel through railways. So this is very important, this paragraph. In order to avoid accidents between the car and train, you need to make sure that both car and train don't arrive at a town X at the same time. So let's say we have 1, 2, 3, and 4. We have a, let's say, road. We have a railway. We have a road. We have a road. And we have a railway. And we have a road. So yeah, so this could be one example of a map where 1, 2, 3, and 4 are towns, and these are given as roads and railways. So what this says, you need to make sure that both car and train don't arrive at town X at the same time. Note that the car and train are not required to arrive at town N at the same time, but are allowed to do so. Okay, so what does this mean? If you're starting from 1, then for a particular town X, you cannot reach by both car and train simultaneously. But for X equal to N, which is the destination, you can do that. You can reach at this point through car and railway simultaneously. That is allowed. But for any intermediate X, for any intermediate town, that is not allowed. Traveling to a different town using one railway, one would always take exactly 1 hour. What is the minimum number of hours needed for both vehicles to reach town N? Okay, so let's say from 1 to N by road, it takes 4 hours. This is the minimum time by road, and by railway, it is taking 6 hours. This is the minimum time for railway. So what is the maximum of these? 6. So 6 will be our answer. Okay, so what we have to do, we have to find the minimum time for road, minimum time for railway, and we have to print the maximum of these two. Okay, how will we do this? Let's consider the test case. So first of all, we want to look at the constraints, as I said. So the first line of the input takes two integers and an m, and n is the number of towns and m is the number of bidirectional railways. And next m lines contain two integers u and v, denoting the fact that there is a bidirectional railway between towns u and v. So, okay, n is from 2 to 400, m is from, like, obviously the order of m is n square. So the order of m is 400 cross 400, which makes it 1.6 10 power 5. Okay, so you can obviously apply BFS and DFS because it takes order v plus e. Okay, that is under the time limit, so you can do that. So now if we see the test case, we have 5 and 5, which is n equal to 5 and m equal to 5. So we have 1, 2, 3, 4, and 5. Okay, so these are the towns. These are the towns. We have a railway from 4 to 2. So 4 to 2 is a railway. 3 to 5 is a railway. 3 to 5 is a railway. 4 to 5 is a railway. 5 to 1 is a railway. 1 to 2 is also a railway. Now, whatever edges are not given here, that means there exists a road between them, because we know that between x and y, either a railway would be present or a road would be present. So between 2 and 3, there is a road. Between 1 and 4, there is a road. Between 4 and 3, there is a road. Right? Between 2 and 5, there is a road. Okay. Between 1 and 3, there is a road. Okay. So it is becoming messy, but okay, you are, I feel you are able to understand. Okay. So now, from 1, both car and railway would be starting, and we want to reach 5. So what is the minimum time that the car takes if we consider the road path? So if we see, we have a road from 1 to 3 as well. So the minimum time taken by the road will be, by the car will be, how much will be the time taken by the road, by the car? Okay. So by what is the minimum time taken by the railway? 1 and 5 is connected directly by the railway. So the minimum time taken by the railway is 1. Okay, that is trivial. That is trivial. Now, if we want to talk about road, what is the minimum time taken by road? So we also have 2 and 5 are also connected by a road. So from 1 we can go to 3, from 3 we can go to 2, and from 2 we can go to 5. So minimum time taken by the car to travel through roads is 3, and we want to output the maximum of these. So maximum of these is equal to 3. So that is why the answer is 3. Okay, so this is basically the question. You just need to find out the minimum time for the train to reach from 1 to n. You have to find out the minimum time taken by the car to reach from 1 to n, and whatever is the maximum of those, that would be your answer. So there is a trick in this question. I will not tell you guys the trick, but yeah, this is a very simple question. Just need to do BFS. But I want you guys to think how you will solve this problem. So it's a bit interesting. Let's see if you guys are able to solve this or crack that trick or not. So yeah, I hope you have understood this question. It's just a very simple question to understand, that do one BFS from 1 to n for railways, do one BFS from 1 to 5 for roads, and whatever is the minimum time for road, note that. Minimum time for railways, note that. Whatever is the maximum of those, print that. That is your answer. Okay, so that sums up today's live session. I hope you guys understood this question, and also this TSU data structure So if you guys want the template, you can message me on Discord. I will provide you. And if you guys have any queries, you can always message me, Satvik, and Atul sir on Discord or Google groups. We're always there to help you guys. So yeah, that's it for today. Thank you. Thank you so much.
The second question.
Sorry.
The second question.
For which week?
Fifth week.
That has been explained by Satvik. So did you join just now or?
No, sir, I joined, but I didn't able to see.
At what time did you join?
5:40 around.
Yeah. So actually, I guess Satvik had explained by that time the question 2.
You can watch the live session on the YouTube. You can go, go back in time and watch my explanation for the question on YouTube.
Yeah, so like this
Okay.
will be shared with you guys on your platform, NPTEL platform, so you can see this has been recorded.
Okay, sir.
Okay.
Yes, sir.
Is that fine? Whoever had asked the question.
Yes, sir.
Okay. Thank you. So did you understand all the questions, DSU and all the things?
Yes, sir. Fine.
Yeah. Okay. Thank you. So we'll close the session now. Thank you so much. Thank you so much for attending.